Welcome. Interpreting derivatives in context is going to be the topic of today's lesson. And yeah, sure, we already know what's the derivative, right? That's the slope of the tangent line. Great. However, in life, in real life, in the first place, that's the rate of change of your function. It shows you how fast your function changes. So, and what's very important, it's instantaneous rate of change, right? Because there's also such thing as average rate of change. We will actually discuss that today. So, if you have a function f of x, and it can be anything, it can be the amount of rabbits in your city, in zoo, right? And that can be position. It can be the amount of the amount of charge flowing through the wire at time t. It can be anything. It can be economics. It can be some costs to produce x items. So some function, and you take f prime of x. It shows you how fast your function changes. That's going to be the rate of change of your function. So it will show you how fast your population changes. It will show you the current, the rate of change of the charge, and so on. So if the f of x, imagine f of x here, let's look at position, right? S of t. If we take the derivative, what's that? That's going to be velocity. We define velocity this way. So velocity is s prime of t, right? The first derivative with respect to time is going to be velocity. What's velocity? Velocity, speed. Yeah, of course, they're not the same. The speed is the magnitude of velocity. However, speed is just something clear, right? Something close to us. So speed, speedometer, right? So you look at that, it shows you how fast your car moves. So that's about rate of change of position. It's always, so remember, derivative, that's about rate of change, instantaneous rate of change, speedometer, right? You look at the numbers, 60 miles per hour, 62, 63, shows you how fast your position changes. Wonderful. Now let's give some example, right? Imagine, let's work with population. So usually, really in this exam, that's also true. The most popular topics are, I think, so biology, that's about population growth or decay, right? It depends on the sign. It will be it can be bacteria, rabbits, it also can be humans. Biology is one of the branches, right, of this context. So we need some context, right? So it's biology, one of the branches. We also have position, velocity, acceleration. We have this holy trinity of kinematics. We'll discuss it even in more details today, right? We'll give it more attention. And third one is economics, I think. And of course, okay, I can even say not even only position, velocity, and acceleration. There's also physics, right? You can work with current. So as I told you, there's charge, some physics, temperature. So it can be physics, biology, and also economics. Takes a huge place here. So of course we will discuss all of them today. At least try to touch every aspect of these branches. Wonderful. So let's start with population. That's also a super popular example. Imagine p of t. Imagine we're given a function p of t that represents the amount of rabbits. So this is the amount of rabbits in some area, I don't know, in some park. So it is represented by the function 3 multiplied by e to the x. And let's try to find the derivative, right? Let's try to find f prime of t, what it will be. It will be 3 multiplied by e to the x, right? Because the derivative of e to the x is e to the x. That's the most weird derivative rule, right? As we remember, nothing changes there. So 3 e to the x. And so what do we see? Of course, it means that our function, that the population grows. Yeah, sure. And actually this type of growth, then you take the derivative and you get the function p of t, because look at that. In fact, that's dp dt. We found dp dt, and dp dt is equal to p of t, right? So this kind of derivative is equal to the function. It's actually very significant result. and we even have a name for that. We call that exponential growth, and we'll talk about it later in the 7th unit, I think. Yeah, we'll discuss it like more closely. So this is about that. Anyway, we found the derivative, and that shows it shows that how fast our function, how fast our population grows. And imagine, anyway, we have some units. That's real life, right? What's really important? Units are actually super important thing here too. So if p of t is 3e to the x, right, and the units are, it truly has some units, rabbits. So of course, we look at the amount of rabbits. Of course, units will be rabbits. So imagine we calculate, oh, huge mistake, of course, t, right? T. Everywhere we have t. In fact, yeah, time, we work with time in life. So it's the most popular independent variable in real world problems, at least. So time, of course, time, p of t, time. And so we see that the units are rabbits. So we can calculate, I know, at some time we can calculate the amount of rabbits. Then we found the derivative. What will be the unit of this derivative? Rabbits or something different? Of course, something different, and I hope you understand that, because it's actually very clear if you look at that. What's derivative? That's dp dt, right? Rabbits divided by, so here, some rabbits, units, rabbits divided by time. And so you choose time yourself. It can be year. Yeah, we can find the amount of rabbits per year. So surely we need to divide by the units of the variable. And for example, it can be year. So rabbits per year, the population, we look how fast we see the growth rate per year, yeah, rabbits per year, some number per year. So if, for example, we say someone wants us to find the population growth, I don't know, in 3 years, then we'll say, okay, that will be 3 multiplied by e to the 3. So that will be some number, truly, and let me actually calculate it. So the answer will be 60.3 approximately. So in 3 years, let's say now it's 2026, so in 3 years, in 2029, the amount of rabbits, yeah, the amount of rabbits in that area will grow with this number. So this is going to be the growth rate in 2029. 60.3 rabbits a year in that area, in some small park. That's it. This is how it works. And that's, of course, let's give more examples, I think. All right, next example. Now we want to work with charge, q of t. So this is the function, q of t. It shows you the amount of charge that flows through the wire at time t. Right, and of course it has its own units, coulombs. Everything will have its own units here. That's real life. We need to measure with respect to something, right? So it's going to be coulombs. I want to find current at time 2 seconds. And if you don't know, I hope you know, but if you don't know, the current is dq dt. That's the derivative of charge with respect to time. That's a physics thing, physics quantity. Wonderful. And first of all, let's actually discuss what's the average velocity, not velocity, the average rate of change and instantaneous rate of change. What's the difference? Because I think that's essential. And let's look at this example. So q of t, right? And imagine I want you to find average current over some period of time. And the thing is, over some period of time, that's about the average rate of change. We want to just take some period of time. It can be not only time, of course, it can be some x, yeah, any variable, but usually we'll work with time. So we take some period of time, we say delta t, t final minus t initial, yeah, we take 2 points, say, in 5 seconds from minus 0. Yeah, we start from 0. And we take 2 points, we take some period of time, we want to see what was the total change, right, in q in these 5 seconds. So, and we want to find dq delta q delta t, right? So we want to find the change in charge. So we take q at time 5. We substitute 5, we get the number, and we subtract, and then we do, so minus, we substitute 0, right? We also get some number. Over period of time, that delta t, that's like 5 minus 0, 5, right? So the whole point is that we take some period of time and we see the total change in that variable over this period of time. We don't really care what was happening there, how fast it was changing, you know, all this stuff. We just want to see the total change. We just see the average change, right? We want to see the total change here and divide it over some period of time. Then we'll see the average rate of change. So this is the concept of the average rate of change. It's kind of clear, I think. Because if you really think about the instantaneous rate of change, it's kind of weird. And the best way to think about the instantaneous rate of change, that's speedometer, right? The example with speed. And if you look at the speedometer, the speed there always changes, constantly changes. But if you, at some moment of time, you see that, okay, it was 65 miles per hour, and you think about it, 65 miles per hour, what do you mean? It's instantaneous rate of change. What do you mean 65 miles in 1 hour? In 1 hour, instantaneous rate of change. In 1 hour, you're saying, this is my speed. It's weird. But don't worry, it just means that if you continue, if you maintain the speed, if you maintain your speed, you freeze your speed, you would travel 65 miles in 1 hour. Because anyway, we need some units. The total difference is between average rate of change and instantaneous rate of change is that, even see here, look at here, you see delta, right? And then we're going to write dt, right? The instantaneous rate of change will be dq dt. So in fact, the average rate of change, which is secant on the graph, right? Secant line, is an instantaneous rate of change. If we shrink the period of time to 0, shrink it really to 0. So if the delta t approaches 0, we're going to get instantaneous rate of change. So this is the idea. This is the difference between them. Therefore, actually, instantaneous rate of change. So this is the slope of the tangent line. This is the slope of the secant line. Again, you know, and using limit, you're going to get here. But the average rate of change also, it's used very often in life. So remember, average rate of change is also very important. But this thing, yeah, of course, that's instantaneous rate of change, and it's kind of important too. So they're both equally important. I can't say something needs less attention, you know. All right, let's remove this now from the board. That was just some small conversation about the average and instantaneous rate of change. So in fact, you just have to understand that instantaneous rate of change is the limit of the average rate of change as the period of time delta t shrinks to 0. All right, let's solve the problem now. So we want to find the current. We want to find the derivative, dq dt. We want to find the derivative, and that will be 3t squared minus 4t plus 6 and plus 0. It was easy, no chain rule. And that's all. So this is the current. We found the function. This is the derivative. Now they want us to find the current at time 2. So what will be the current? Current will be, we just substitute 2, right? Which is 3 multiplied by 2 squared minus 4 multiplied by 2 plus 6. So let's remove zeros. So it will be 12, right? Minus 8, so it's 4 plus 6, 10. 10. And what are the units here? As we remember, yeah, we have to work this way. Coulombs over time. Time in seconds. So it's going to be coulombs per seconds. Okay, seconds, just seconds. Right, and we also have a different name for that. In physics, coulombs per seconds are called ampere. But of course, that's not super important. You can also write it down this way, it's going to be fine. So But the main thing is that it's not just 10 coulombs, okay? The rate of change has its own units, its own unique units. So it's coulombs per seconds. I hope that's clear. Next example. All right. Now, the whole trinity of kinematics, right? So it's position, velocity, and acceleration. And it doesn't really differ from the things we discussed previously, the growth rate and the current example. Yeah, they are all similar. I mean, it's all about derivatives again, but that's just something, I can even say daily routine. Yeah, you meet it really every day. Position, velocity, and acceleration. So, okay, position stays here. Velocity was defined as the rate of change of position. So it's just s prime of t. And then I was thinking, yeah, kind of interesting to look at the rate of change of position. Great. But maybe it's also interesting to see how fast our velocity changes. Yeah, sure. Let's also see. And we decided to call this quantity acceleration. And that shows how fast your velocity changes. Acceleration shows you how fast your velocity changes. Yeah, we could also then say, okay, maybe let's then also consider the rate of change of acceleration. We could also do that, right? And that would be some quantity Camille. Yeah, I don't know. But we stopped. So that was all. That's the end. We have position. Velocity is the rate of change of position, and then we have acceleration. Acceleration is the rate of change of velocity, and we can also write it down in terms of position. Yeah, so it will be s double prime of t. So this is all. Yeah, this is how they are linked. This is how they are connected, and that's all basically. The only difference between position, velocity, and acceleration is that you'll here see sometimes the second derivative, right? In some problems, you'll have to find the second derivative of position, because in previous problems, no, that usually will be just one first derivative and that's all. But here, yeah, you can also see the second derivative. Now let's look at the example. So here's the example. S of t equals t cubed minus 6t squared plus 9t, and that's all. Meters. So the units are meters. And we want to find what? I want to find velocity, acceleration. Okay, let's find velocity, acceleration as a functions, right? And then also velocity at time. 4 seconds. And also acceleration time 3 seconds. So good. Let's start. First of all, in order to find velocity, we have to find s prime of t, right? We need to find the derivative, take the derivative. That will be 3t squared minus 6t, oh no, not 6, 12t plus 9. That's it. So this is our function, velocity, finished. Acceleration is derivative of velocity, v prime of t, or s double prime of t. So now we're going to take the derivative of this function. So that will be 6t minus 12, the derivative of a constant 0. So this is it. We found s and v and acceleration. Everything is here. Now we want to find, by the word, what are the units of velocity? So velocity is ds dt. So it means time here everywhere in seconds. So that will be meters per second. Is that logical? Yes. So in order to find the units, apply this logic, okay, every time. Just write it down. This ds dt, right? You look at that, you see, okay, this is in meters, this is in seconds, meters per second. Okay. If you have average, if someone wants you to find average velocity, in fact, the same thing, but you'll have delta s, right? Delta t, nothing changes. Here on the top you have meters, on the bottom you have seconds. So the same thing. Every time just look at I can say, okay, it's kind of definition, right? Look at definition, look at the formula, and you'll find your units. Meters per second, that's about velocity. What are the units of acceleration? Acceleration is dv dt. So on the top we have meters per second, and we also have to divide by seconds. So that will be meters per second squared. Okay, so that's very, very important. That's really important. All right, so now we want to find the velocity at time 4, and that's not a problem. Velocity at time 4 will be, we have to substitute 4, and we will get 3 multiplied by 16 minus 12 multiplied by 4 and plus 9. And that will be, so what's that? That's 48. That's also 48. Right? Funny. Yes. So the answer is 9. 9 what? Meters per second. This is the velocity at time 4. Oh, good. Now we want to find the acceleration. And the acceleration is going to be 6 multiplied by 3 minus 12. And that will be 6. What are the units? Meters per second squared. So this is the end. Very easy. As I told you, nothing is really hard here too. Everything is the same. I mean, and the derivatives will be really simple there in these problems. So believe me, that's not hard. Let's actually find the, now let's find the average velocity over a period of time from 0 to 7. Say I want to find the average velocity on this interval, right? So average velocity, that's always about some period of time, some interval. So what's the change in time? So again, it's delta S delta T. So what's the change in time? The change in time is 7 minus 0, 7. What's the change in position? I don't know, we have to substitute 7. And then, so it will be minus 0. Actually, I don't want to do that. Of course, at time 0, the position is 0. But, so we need to find S of 7 over 7. We need to calculate this. Okay, let me calculate it. So the answer is 16. meters per second. Again, delta S over delta T. Meters, seconds. Meters over seconds. Meters per second. That's all. Now I think we can switch to economics, right? And that will be the final branch. Or actually a small wrap up, right? So let's also talk about graphs a bit. So yeah, and we will actually work with, again, position, velocity, and acceleration. So if this is your position time graph, yeah, position also sometimes might be called x, right? Instead of s, use x, just like with respect to some axis, x-axis, right? Position, x-axis. All right, so ST, position time graph, and this is some, I don't know, curve. Okay, let's use blue too. Okay, actually, let's use red. So it's some curve. Okay, it's too beautiful. This is some curve. This is your position time graph. And what is the slope? If you find the slope, for example, here, if you want to find the slope at this moment, at this point, and you find the slope, right? What's that? That's gonna be velocity, instantaneous velocity. So at some point, let's say that's what? 3 seconds, right? It's in seconds. So at 3 seconds, what did you find? You found the velocity, instantaneous velocity at time 3 seconds, all right? So the slopes here are velocities, instantaneous velocities. And if you take the secant line, right? For example, you find the secant line, you will find what? You'll find the average velocity on this period, on this interval of time, right? Over this period of time, some, let's say 6. So the slope of this line, the slope of the secant line, will be the average velocity. The slope of the tangent line at some point, right? That's going to be the instantaneous velocity. And the same thing, of course, works if now you have here velocity, right? Velocity time graph. Then situation changes and it will be acceleration. So here you'll have the tangent line, right? If you want to find the tangent line at some point, you're going to find the acceleration, instantaneous acceleration at some point. If you take the secant line, right, you're going to find the average. If you take the slope of the secant line, you find the slope of the secant line. You're going to evaluate the average acceleration over some time interval. Do you understand? So of course, remember the derivative is both the slope of the tangent line and plus it's of course the rate of change of a function. So the slope of the tangent line, the rate of change of the function, they are like yin and yang, okay? They are the same thing. And what else? An average rate of change, right? Average rate of change. Graphically, that's the secant. What's that? That's the slope of the secant line. Now I hope that's clear. That's a dot. All right. Now economics. All right. Now a bit of economics. Right, so first of all, here we have two main heroes, let's say. The costs, right, so it's just amount, so that's the cost to produce, I don't know, X items, right? And we have revenue. That's the revenue you get from selling X items, right? So costs for X items to produce X items, and revenue, that's where everything gets really well. That's revenue from selling X items. I just mean in terms of problems, right? In problems, usually will see these two things. And they also have their own derivatives, of course. And derivatives are called marginal cost and marginal revenue, respectively. So this is going to be, so this cost, marginal costs, this is revenue, and R prime of X is going to be marginal revenue. Yes, so in fact, these are costs to produce X items, right? And this just shows what's the average rate of change. So this instantaneous rate of change of your costs, right? It shows how much cost you need to produce one more item. So it's like average rate, it's not average. It's rate of change of your function, instantaneous rate of change of your cost function. And the same thing here, it shows you how much more it will bring you, one more item will bring you. It shows you what is the revenue this one more item will bring you. That's it. R prime, C prime. And in fact, that's all. Of course, sometimes you might see also such thing as profit, but it's I don't think there's a huge probability of that. That's revenue minus costs, right? Profit, revenue minus costs. And also sometimes you can see marginal profit. And what's that? Think about it. That's just the difference in marginal cost and revenue. So instead of just revenue minus cost, you're going to get R prime of X minus C prime of X. And that's it. That's all. And that's it. So these 6 things will be enough. That will be enough to cover and solve all the economics problems. So let's solve one for costs. And I think then we are going to finish the lesson. Right, so let's work with costs now. Let's keep it here, I think, this part. All right, costs. So we see the cost to produce X items are 0.01x x cubed minus 0.6x squared, and what's there, plus 13x. And we want to find the volume. No, what? Find the marginal cost at x10. And what else? That's all. So I want to find the costs. What? Just too boring. Sounds like a boring thing. No. We want to find what? We want to find marginal costs. So at least something. Marginal cost. So this is what it is, right? Costs. Nobody said to find S prime here. So you have to understand. Yeah, you have to be able to interpret the word marginal cost into the fact that you have to find the derivative of cost, right? Marginal cost, the derivative of cost. So that's your cost function. And you need to find S prime of X. That will be the marginal cost. And then we'll substitute 10 and we'll obtain the marginal cost for X items, right? At X10, right? All right. So this is going to be 0.03, x squared minus 1.2x plus 13. So this is it. This is our marginal cost function. The rate of change of your costs, right? Shows you what are the costs for one more item, to produce one more item. And if we substitute 10 now, that's going to be 0.03 multiplied by 100 minus 1.2 multiplied by 10 plus 13. So that will be 3 minus 12 plus 13. 4, right? So 3 minus 12 plus 13. Yes, 4. So the final answer is 4. And let's actually deal with the units. We're not given units. Let's say the costs are in dollars. Then the marginal cost. So what's the marginal cost? That's dc dx, right? That will be then dollar per some widget, the item. Okay, so these are the units of marginal costs. And here the same, $4 per item. So this is the answer. Okay, let's solve one more, and that will be the end. All right, so last example. Now we're given a profit. All right, so profit, P of X, equals this. And we want to find the marginal profit at X50. So it means the hardest part is to interpret the marginal profit, and that's P prime of X. We want to find P prime of X. First of all, and then we'll also want to find P prime of 50. Yes. So let's start with this one. What's the P prime of X? That's easy again, the super boring derivatives. 0.06 x squared plus 100 minus 0. Right, so that's it. This is our marginal profit. What are actually, again, in fact, this is, if this is in dollars, then this is dollars per item. Nothing has changed. So this is our function. Units are per item. And now we want to find at x50. So we want to substitute 50, we will get 0.06 multiplied by 50 squared plus 100. And that will be 0.06 multiplied by 2,500 plus 100. And that's going to be negative 50. And you know what it means? It means that company has big problems. Kinda. That it doesn't mean that the profit, there is no profit at all, right? It shows you the rate of change. It shows that actually they have really negative trends right now, and the profit is decreasing. At moment 50 items, at moment they produce 50 items, the profit decreases. At the rate of change, the profit goes down. So, but it's not zero yet. Maybe. I hope so. But the problems, yeah, surely there are some problems for the company. Alright, that was all for today. See you in the next lesson. Smash AP. Happy studying.